Hi grade 10s, hope you're doing okay. I'm going to start with quantitative chemistry. Okay, so what this is remember the word quantitative is looking at numbers and values. So this is going to involve maths in chemistry now, okay. This is one of the nicest sections though. I think a lot of the girls like it. So if you just please listen to what I want to say, and please watch these videos over and over and over, okay, if you're not understanding. Okay, I'm trying to say as much as I possibly can in all my videos. So please make sure you hear and make a note of everything that I'm saying. All right, so the first thing is, this is your molar mass. So I'm not really going to worry too much about this because you have done this, the molar mass. I'm just quickly going to run through the definitions and reminding you of what to do. This is an extremely important part of quantitative chemistry, so I need you to make sure you know how to do this. So we call it a whole lot of stuff, okay? Molar mass, relative atomic mass, and yeah, let's talk about the relative atomic mass. So the mass of an element compared to carbon, that's why it's called relative, because it's relative to carbon. And what they did was they took carbon and it was given the mass of 12 grams, and that's where the 12 comes from on the periodic table. And then they compared all the other elements to carbon, and that's how they got all their relative atomic masses. Okay, and it actually has a weird unit. It's actually got a atomic mass unit. That's what it stands for. That's atomic mass unit. So it's very original and creative. So it's atomic mass unit, and it basically just means 23 grams. Okay, so sodium is 23 AMU, and it means 23 grams. Okay, now what we are going to do is look at the molar mass. Okay, now molar mass is the mass in grams of 1 mole of that substance. Now please don't get your knickers in a knot. 1 mole, you haven't done a mole yet. Okay, it's not a thing on your face, and it's not an animal in the garden. It's something else, okay, and we're going to get to it on page 3. Okay, so don't worry about that now. Just learn the definition as it is, okay? And it is the same value as the relative atomic mass. Remember, I said to you, everything with the word mass in the periodic table means the same thing. So, but now the atomic mass unit is actually equal to grams per mole. Okay, grams per mole. Okay, so this is a quantity of something. So however many moles we have, it's 1 mole to give you those grams. So 1 mole of sodium gives us 23 grams. Okay, so that's what it means. 1 mole of sodium equals 23 grams. Okay, that's what it means on the periodic table. Again, don't stress about the mole just yet. Just use it as if you know it now. Okay, but I'm going to explain it to you on page 3. Okay, so this is the molar mass. You do it exactly like we've been doing it. So for example, here's water. Water is 2 hydrogens. So we know the atomic mass is 1 times 2 because there are 2 of them, plus the 16, which is the molar mass of oxygen, or the atomic mass. Add them together, but this time I want you to put a proper unit. So it's 18 grams per mole. Remember, no unit, no mark. I've been very lenient with you lately, especially with waves. I marked you correct, even though you didn't put joules for energy or S for seconds, but I'm not going to do it all the time. Okay, so be careful. Sodium chloride. Sodium is 23 on the periodic table. The mass, please don't get confused between the mass, atomic mass, and the atomic number. It's the mass number. Okay, so just double check all the time. It's always the bigger number. All right, plus the 33.5 from chlorine, and that's giving us a 58.5 grams per mole. Okay, a molar mass does not depend on the number of compounds. So I could have 50 sodium chlorides. The molar mass is still going to be 58.5 because we are looking at it as a gram per mole, which comes from the periodic table. Okay, so we're eventually going to be using this in chemical equations, and you know that you have the big numbers in the front of a chemical equation. I'll show you just now when we're going to balance. So only the number of atoms in a compound, i.e. ignore the big numbers in front of the compounds. That means when you work out the molar mass, you're not always going to ignore the big number. I'm going to show you when you're going to use the big number. But for now, for the molar mass, you never look at the big number. Okay, very important. Okay, even matrics forget that. All right, so balancing chemical equations. Firstly, I just want to remind you on how to write a chemical formula. So remember, you need to know your periodic table and how to use it. You need to learn your polyatomic ions. And we do the switcheroo. I've decided to call it the switcheroo because I like it. Okay, so it's better than cross multiplication. I mean, how gross is that? Okay, so for example, sodium hydroxide, I have a sodium that is in group 1, so I get a +1. I have a hydroxide, which is a polyatomic ion, where I've learned it off by heart, and I get a -1. And so we put it underneath there without the sign, so it's a 1 and a 1, and then we swap them. So sodium hydroxide is actually Na1OH1, but we ignore the ones. Okay, aluminium sulfate. Aluminium is in group 3, so we have a 3. Sulfate is a -2 because I've learned it off by heart. And we put them underneath, and then they switch. So can you see that aluminium here gets the 2, and sulfate gets the brackets, remember, because it's one whole unit. Because of the polyatomic ion, we treat as a 1 unit, and there are 3 of them now because they have swapped. Okay, and there we have the rest of it. Please just remember, if you have an ide other than hydroxide, this is not a polyatomic ion. A sulfide with a D just means sulfur, or a nitride with a D just means nitrogen. But anything with the T, it's probably your polyatomic ions. Okay, so writing the formula, or formulae, sorry, that's more than one formula of the following compounds. So remember, this is called stock notation, where I put it over there. So I'm telling you now that actually has a charge of +3, but I'm not going to show you the charge. I'm just going to put the value underneath. Just ignore the sign for now. And my Br, which is bromide, so it's just bromine, okay, but when it's in a compound, you change it to a bromide. Okay, and that is in group 17 or 7, and so it will get a charge of -1. And so we cross them and we land up with, Cu1, don't put it, Br3. Okay, if you do happen to put the 1, it's really not the end of the world. You won't get it marked wrong. Okay, so that's what we do it. And remember, copper is usually a +2 if I don't tell you that. Sometimes copper could be a 1 as well. So the stock notation overrides the rules from the periodic table. Okay, remember copper was a transition metal, and normally all transition metals get a +2 charge except silver, which gets a +1, unless we have a stock notation. Okay, so calcium chlorate. Okay, chlorate is, so calcium Ca chlorate. Oh my gosh, I'm sorry, I've actually forgotten what chlorate is. I think it's a 2. Okay, so it's a -2, I think. And this is a +2. I don't know, one of you will check me, I'm sure. Okay, which means it goes CaCO3. Okay, so I'm hoping it is a 1-to-1 ratio. Notice it's 2-to-2, but we always take it down to its simplest ratio. Okay, then let's look at sodium ethanoate. So sodium and ethanoate is CH3COO, and this is a -1. You can put the value, the sign if you want to. This is a +1, cross multiply, and this one's a little different. The organic stuff gets written first. So, but if you don't write it first, you will not get marked wrong. Okay, so it's again 1-to-1 ratio, so it's written like that. Don't worry if you put the Na in the front, it's really okay. Okay, page 2, balancing equations. Okay, I'm going to quickly go through some of these, and I want you to try some for me as well. You guys did an awesome job last year doing balancing equations, so I just want to refresh your memory. I'm going to do 1 or 2 of these, and then I want you to try them, please. I will give you the memo to this at the end of the period. Okay, so we have, which one should I do? Let me just do this first one. Okay, so remember, you are looking at the elements on this side, and you're looking at the elements on that side. Okay, and we can see that we have 1 sodium, 1 sodium. Yay, that's balanced. Let's look at our magnesiums. 1 magnesium, 1 magnesium. Oh, this seems easy. 2 fluorines, only 1 fluorine. So remember, you take your pencil now. If you really have to use dots, you really can use dots. Okay, but I'm going to use it. So we take a pencil and we go, okay, I'm now going to put a 2 there. I'm sorry, it's a terrible 2, but anyway. Okay, so that means it multiplies in, remember? So that means we get in 2 sodiums and 2 fluorines. So that sorts out our 2 fluorines, but it now unbalances our sodiums. So in order to fix that, I put a 2 there. Please, please remember that you cannot change what these are. You've learned now how they need to bond. So you cannot change how magnesium and fluorine react. You can't change how sodium and fluorine over here bond. You can't put a 2 in the front there. You know it won't work. Just to balance that, the only thing you can do is add whole one of those, and by putting the big numbers. These are the big numbers that I was talking to you about. I don't know if you can see the 2. Sorry, my pencil's running out of lead. Okay, so we've got a 2 there and a 2 there. That is balanced. Okay, that's all you need to do. All right, try 2 and 3 for me. I'm going to, after this, I'm going to show you maybe 4 and 5 quickly. Okay, so these now, yes, aren't I mean? I now give them to you in words and you have to come up with them. All right, so again, remember, ide means it's sulfur by itself. So this is an iron sulfide. That's because it's a -2 and a +2, so they are 1 to 1. HCl is hydrochloric acid. That you'll eventually just learn. Okay, hydrogen sulfate. So sulfate is a SO4. Okay, hydrogen, sulfate has a -2, hydrogen has a +1. So we're going to need 2 hydrogens with the sulfate. And we're going to need an iron chloride. So remember, iron is a 2, chlorine will be a -1. And so we're doing that. So let's see how we're going to balance this. So we've got our ions are balanced. Okay. Sulfurs are balanced. Hydrogens are not. So let's put a 2 in front there. That means I get 2 hydrogens, 2 chlorines. Perfect. We are balanced. Oh my gosh, wait a minute. What happened to oxygen here? Okay, something really went weird here. All of a sudden I've got a sulfate. Let me just think, what do I need to do here? Oh, you know what? I think this is an ide. Okay, hydrogen sulfide, that would make sense. Okay, and it is the right reaction. So that would make sense. Sorry, just cross out the 8 and put an ide. Okay, and then just cross that out there. So it still works perfectly fine. It's just not with the oxygen over there. Okay, so bear that in mind. Okay, so it's only that 2 because the hydrogens are balanced and the chlorines. If you're finding that one of these are not balancing, check your formulae again. Remember, each one of these is a formula. So check them. If a formula is not correct, then you can't balance it. Like I just saw now, I don't have any oxygens on this side. Something's wrong. Okay, so check your formulae again. Let's do this one. So copper is just an atom. So it's just a copper atom. Silver nitrate is AgNO3. Gives me silver plus copper nitrate is Cu. And there are 2 nitrates because nitrate is a -1 and copper is a +2. Okay, so that means I'm going to have to double up on my nitrates here. Remember here, this is nice because you can treat this nitrate as a whole nitrate. It hasn't broken up. Okay, and then we've got 2 silvers over there. And there we have our balanced chemical equation. 2 nitrates, 2 nitrates, 2 silvers, 2 silvers, 1 copper, 1 copper. Perfect. Okay, I want you to try number 6. But what I'm going to do with you now quickly is to show you how and why now, how can I prove that this is balanced? So we're going to look at the molar masses of the reactants and products from reaction 5 or equation 5. So copper, I just need a periodic table. Luckily I have one on my computer. Okay, so copper is 63,5. So Cu is 63,5 grams per mole. Okay, I hope you can see that. Then I'm just looking at the reactants. Now, be careful. In this case, I am going to times by 2 because I just want to show you why it is considered as balanced. Okay, the mass is conserved of both sides, but we don't normally, to work out a molar mass, we will never use that 2. Okay, so I'm actually going to go the molar mass of silver nitrate is 108, plus nitrogen is 14, plus 3 times oxygen's at 16. Okay. Oh, I've lost my calculator. I wonder where it is. Oh, crap it. Seriously, I don't know what I've done with my calculator. Oh, wait, I dropped it. It's on the floor. Okay. I think my cat knocked it off. All right, so 108 plus 14 plus 3 times 16. Okay, 170. Okay, but now that is the molar mass. Okay, so I don't want you to get confused here. This is the molar mass, grams per mole. Okay, but because I want to prove that there's the conservation of mass before and after a reaction, I am going to times it by 2 for now. Okay, so to prove conservation. Now, conservation in science means the same before as it is after. Conservation of mass. We are going to say 170 times 2. And we get that 2 from there because it's 2 of those that makes this balanced. But remember, if I'm asking you a conservation, if I'm asking you for molar mass, that's where you stop. Grams per mole. Okay, that is a molar mass. This is only to prove conservation of mass. Do we do that? Okay, so that comes from that. Okay, so these are our reactants. So let's get our total. Let me use the pen now. So we know that it's 170 times 2 plus the 63,5. These are the reactants. Okay, so that is plus 63.5. Okay, we'll soon know if my calculations are not right because it won't balance. Okay, so that's my reactants. Then we're going to look at products. Okay, underneath here. So let's take a look on our products. We have silver. Okay, silver is again 108, but there are 2 of them here, so we're going to do that. We've got copper. Over there, copper again is 63.5. I think you can see where this is going. Plus nitrogen. Okay, wait, there are 2 nitrogens, remember, because there's there. So 2 times 14 plus, now remember, there are 3 oxygens for every 1 nitrate, and there are 2 nitrates. So together we have 6 oxygens. So 6 times 16. Okay, so product, we are now going to add all of those up. I'm going to have to restart this video if this doesn't work, because that's going to be embarrassing. 63.5 plus 2 times 14 plus 6 times 16. And we have 403,5. Yay, sure. Okay, so what have I done here? I've taken the reactants here and the number of reactants, and I've added up their masses, And I've taken these and I've added up their masses, and I've shown you that they are balanced, because there is always a conservation of mass before and after a reaction, if it's a closed reaction. Obviously, if you are letting gases escape, those gases are going to take away some of the mass. But if you've got a closed container, you're going to do this. Okay, so there it is there. Remember, molar mass, we would only, if I ask you for molar mass, it would only be AgNO3. The only reason why we times it by 2, please listen to me, the only reason why we times it by that 2 was to show the conservation of mass. Very, 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 very important. Please don't do it ever. Molar mass is never using the big one. Okay, please. I can't tell you how much I need you to do this for me. Okay. All right, so I'm going to show you waters of crystallization now. Okay, so I'm going to blow your mind now. Okay, so you know the blue crystals that you always use, and we always call it copper sulfate, and there's these lovely blue crystals, and we like to play around with them and make blue solutions. Okay, so the blue, and they, oh man, I keep doing that. The blue crystals are actually copper sulfate, but there are some water molecules that are stuck in between the copper sulfates. And for every 1 copper sulfate, there are 5 waters. This is the only big number that we consider for the molar mass. Let me say it again. This is the only big number we consider for molar mass, is when you have a water of crystallization. So we can dehydrate copper sulfate. And if I was at school, I would show you. You take the blue crystals and we just heat them, okay, and you'll end up with a white powder, and that is just copper sulfate. So you're removing the water, you're dehydrating it, and you just get copper sulfate. So there's words for this. So a hydrous copper sulfate, think of the word hydrous, it's meaning water. Hydrous copper sulfate are blue crystals, and it's CuSO4.5 waters. Just one thing, this isn't the only substance that has waters of crystallization. Okay, so just bear that in mind. Anhydrous means no water copper sulfate, and that's a white powder, and that formula is just CuSO4. So how do you calculate the molar mass of hydrous copper sulfate? So CuSO4 5 H2O. Now, like I said, this is the only time you use that big number because it is part of the formula. It's not here to just balance a chemical equation. All right. So it's part of the formula. So you do this. So copper is 63,5 plus sulfur is 32 plus we have 4 oxygens at 16 grams. Now, plus, you're always plussing, even though that looks like a multiplication, this is not maths, we don't do that there, okay? That just shows you that it is a separate part of this component, of this whole compound. There are 5 waters, so there are 5 of 2 hydrogens that each have a molar mass of 1, or an atomic mass, plus 16. Okay, if you do it like this, you're never going to get wrong. And then just plug the whole thing in your calculator exactly like that, and you won't get it wrong. Okay, my suggestion is to always try and do these complicated calculations twice in a test so that you know that you're okay. All right, I'm going to show you. Can you see it there? Okay. So we have 63.5 plus 32 plus 4 times 16 plus... So we're really just adding all the masses, okay? If you feel like you want to say 1 plus 1 plus 1 plus 1, and that's 10, that's perfectly fine. You can technically do the maths here where you go 5 times 2 is 10, 5 times 16 is whatever, okay? And I'm not going to worry about putting the 1 because I think we're all okay that 2 times 1 is 2 plus the 16. All right, and I'll end up with, and you can double check me as well, 249.5 grams per mole because it is a molar mass. All right, so what you could think of as well is you go, okay, well, what is copper sulfate without the water? How much does the water take up of it? What is the ratio? If I was to work out 5 waters and subtract it from that, I'll get the copper sulfate, the anhydrous copper sulfate. You can work a lot with this. All right. So I would like you, here's the conservation of atoms in a chemical reaction, hence balancing equation. This leads to the principle of conservation of matter and the ability to calculate the mass of the products and reactants. That's what we did here. Again, molar mass, ignore, but for purposes of showing how the mass is conserved before and after a reaction, you will then use it. Okay. So I would like you to please try Think Tank 1, page 241, number 2. And yeah, let me know how it's going and if you need any assistance. Right, and we're going to deal with the mole, tomorrow. Okay.